This is the final lesson of chapter 11 and the final lesson of year 12 mechanics. And the LI is to be able to use calculus to derive the constant acceleration formula. And what we mean by the constant acceleration formula is the TBAT formulas. So we looked at those back in chapter 9. And so those are our formulas. We've got 5 of them that we use when we've got constant acceleration. And we're going to see how we can derive them now. We did look at deriving them in a different way back in chapter 9. So our question says a particle moves in a straight line with constant acceleration a meters per second squared. Given that its initial velocity is u and its initial displacement is 0, prove that the velocity is v equals u plus at. So we've seen that before. That's one of the TBAT formulas and we need to prove it. Well, if I'm trying to work out what velocity is, we said that if we've got displacement as an s, velocity and acceleration, to get from displacement to velocity, I differentiate with respect to time. To get from velocity to acceleration, I differentiate. To get from acceleration to velocity, I therefore integrate, because I'm going backwards. And again here, I'm going to integrate to go from velocity to displacement. So here we are told that there's constant acceleration. So I know the acceleration is a, and I want to work out the velocity. So I'm going to say, well, the velocity is just the integral of the acceleration with respect to time. Well, if I just got to integrate a with respect to time, that's like just some random constant because it is constant acceleration. So what I do is I'm going to say, well, if I integrate that, I'm going to add a t to it. I'm respecting with respect to t, but then plus some other constant on the end. So I've integrated a to get at plus c. And I know that at time equals 0, the velocity is equal to u. We were told that the initial velocity is u meters per second. So when t is 0, v is u. I'm going to sub those things into here. Well, v is u. A times 0, well, that's going to disappear. So I get that c is equal to u. So therefore, my formula for velocity is v equals c is just u. So I'm going to put that to the front, u, and then plus on that at. And we've just proved that first TBAT equation. I'm going to highlight that here. And so we got there by integrating the acceleration. The next bit wants us to prove the displacement is s equals ut plus a half at squared. Well, I'm going to do a similar way. I've now got the velocity, so I just need to integrate it to get the displacement. So I'm saying displacement is equal to the integral of velocity with respect to time. But I know actually the velocity is u plus at, so let's sub that in there. The integral of u plus at with respect to time. Well, let's do that then. Keep these s's in. That is like just a random constant, so I just like I did before, going to stick a t on it, ut. Then here I've got at, so I increase the power to squared and divide by 2, so I'm going to plus a half at squared. And don't forget, I'm still going to need a plus c on the end. Now we do have some conditions. At t is 0, I know that the displacement in the question is 0. The initial displacement was 0 meters. So at t is 0, s is 0. So let's sub that in. S is 0. So u times 0, that will disappear. A times 0 squared, that will disappear. And so I get that c is equal to 0. And therefore, that's my final answer. S is equal to ut plus a half at squared. C is equal to 0, so I don't need to include that. And there we've just proved that TBAT formula for displacement. And we did that by integrating the velocity, which we'd found in part A. Okay, you should be able to have a go now at the very final exercise, which is exercise 11E.